Hey everyone. So this little video is to highlight some of the key concepts and kind of insights I wanted to make sure that you took away from the electric field lab 7 that you did last week, or Monday night, or whenever you did it, right? The the key thing, I guess, to start out with, is this idea that there's an analogy with with gravity that they're building on. And the reason for this analogy with gravity is because then you can think about things in terms of height, which makes it much more visual and much more tangible when we get into the abstractness when we get into the abstractness of electric potential, which is a little bit harder to visualize. Okay, so the idea of those first questions, just to really focus and summarize that, is to think of the idea that just think of the idea of a contour map, which I'm guessing that most of you have seen some version of this, right? So, like, for example, so again, I guess I don't need to say analogy again. So a contour map, the whole idea of a contour map is to be able to visualize something that's three-dimensional on a two-dimensional surface, right? So for example, you might, if you were trying to picture an island that has a mountain in the middle, and if you looked at it from the side view, I'll go back to the side view in a minute, but if you're looking at it from the top, so let's do top view, what you would see is something like there's water on the outside, but then let's say this is the boundary where the island starts, and out here is all water, right? And this line that I just drew represents sea level then, right? So this line is sea level. And then if you want to show lines that indicate all the places that are, say, 10 feet above sea level, you might draw a line that, let's say here, here it was flatter maybe, and then here it got really steep, let's say. But that line, and I'll put that in here, that line represents 10 feet above sea level. Okay, all of those points, what makes that line is it's all the points that are 10 feet higher than all of these points, which are at 0 feet above sea level. Okay, so the contour of that line is what indicates, how far you had to go inland, say. Like here, you didn't have to go very far to go from 0 to 10 feet, so that's a fairly steep place. Whereas here you had to go a long way to go from 0 to 10 feet. And so that's a more of a flat place, right? So the spacing between, right, those points is what indicates the steepness of it. Does that make sense? So, and if I go back to this, so then maybe if there's a peak, say here, if you see a spot where the lines start getting really close together, like this, where maybe I won't be able to draw all these in, but maybe the next one in, let's say this one is 100 feet, and maybe this last one is, this one, I'll just point to it. Let's say that one is like 1,000 feet, and that would tell you that there was a really steep slope here. Okay, so that's a contour map. And so that analogy is what we want to build on. So what they're talking about, let's see if I can make this move here. What they're talking about with those first few questions is to build that analogy up in your mind so that you think about the fact that, okay, these are places where the height is constant, those are also places, let me just write this stuff out now. So if the height is constant, then that means that the gravitational potential energy is constant, right? Because hopefully you remember, gravitational potential energy is given by the mass of the thing times little g times the height relative to some reference point like sea level. Okay, so if the height stays constant, then that means that the gravitational potential energy stays constant also. Okay, so now what I want to build on with, and while I'm at it, let me just mention one more thing. So that's gravitational potential energy. We can define something called just gravitational potential without the energy part, and we define that to be gravitational potential energy per unit mass. So it just makes it more generic. It makes it something that you can talk about independently of the particular mass that you choose to move around in that spot, right? So I can talk about, so in this particular case, this is just equal to G times H, right? And that's cool and useful because these lines on the contour map, this is a line of constant height. It's also a line of constant gravitational potential because potential is just little g, which is 9.8, times h, which in this case is 0. So this line, this sea level, we could call this a line of constant gravitational potential, right? And this is also a line of higher constant gravitational potential. In this case, it's 10 feet converted into meters times 9.8. In this case, it's 100 feet. See what I mean? So the connection here is to build your awareness that potential, gravitational potential, and height are basically the same thing, except for they're proportional to each other, and the units just work out by multiplying by little g. Okay, and then one more piece to this, which is that the gravitational force or the gravitational field. So gravitational force, I'm gonna just write field. So gravitational field, which is equal to the gravitational force per unit mass, in the same way that electrical field is electrical force per unit charge, because mass is like the charge for gravity. Okay, so gravitational field, which is basically gravitational force divided by the mass, is going to be equal to, I don't want to say equal to, it's going to be, I just want to make a statement about it, which is that it points downhill. And by downhill, I mean toward lower gravitational potential. So it's just trying to build, all those questions in that part of the lab are just trying to build your intuition about the fact that if I make a line for that, if I know what the gravitational potential looks like, and I have those contour lines, then I also know what the gravitational field looks like. The gravitational field just points downhill in potential, which means, like the gravitational field would be pointed this way, from high potential to low potential, from high to low, from high to low, from high to low, and so on. Okay? And so then all of that just completely carries over when we talk about electrical potential. It's going to be almost exactly the same thing. We're just going to replace all of the, things, the electrical version, I cannot spell, electrical version is just, you can do the same thing, and you can map out what the potential looks like, and then it's just called electrical potential rather than gravitational potential, but the relationships are the same, right? So electrical potential energy equals electrical potential, which is what we usually call voltage, divided by not the mass, like in gravity, but the charge. Okay, so then we can make these same kind of maps, right? I could do the exact same thing as I did before. I could have a place where this is 0 volts, and then this could be the line for all the places that are, this could be 10 volts, and that could be, that one could be, say, 100 volts or something like that. And then these lines are called equipotentials, because it means equal potential, right? All the places that have the same potential. Okay, so that's the picture of that. I'm going to stop there for now and maybe make a separate video for anything else I want to say about this, but I think that'll at least give you the kind of grounding in the core concept.